Okay, I think we can get started. Any questions before we get going? Okay, our first exam. Guess we have to have exams, right? College. 2 weeks from today. So we'll cover everything that we go through the end of class next week. All right? I'll give you some more info next week because I haven't really thought that far ahead. I just know that in order to space things out properly this semester, we're going to need to do an exam in the next few weeks. So I think 2 weeks will probably work for it. So it's going to cover properties of water, relationships between surface water and groundwater, what we've been going through, and then however far we get next week. Okay? All right, so what I want to do is continue on talking about how surface water and groundwater are related, and then we're going to move on to only talking about groundwater the rest of the semester. So we'll try to finish up the surface water, groundwater stuff today. I didn't get quite as far along last week as I wanted to, so we're going to go back and look at something that we finished last week. So we were talking about what we were calling the Baseflow recession equation. This is an extremely useful mathematical expression for looking at how groundwater and surface water interact with one another. So let me just sort of draw out where we were. So it's based on something called a hydrograph for a stream, which is a graph of Q, which is discharge, which we typically measure in either cubic feet per second or cubic meters per second, and then time. And for these Baseflow recession equations, we usually look at a year. We're looking at how the surface water and groundwater interact with one another over the course of a year. Okay? So in most places where you have snowmelt or a wet season and a dry season where the streams get swollen in one part of the year and then the stream flow drops through the rest of the year, you might get a hydrograph that will look something like this. Okay, so those might actually be measurements of stream flow taken over that time. So a couple of points on the graph here that are important. The highest point that your stream flow reaches in the spring is what we're defining as Q naught. Q naught is the discharge at the start of the recession. And then, let's see, what's the best way to do this? And that Q naught occurs at a certain time, which is the start of the recession. And what we do is we try to find a mathematical expression that represents a best fit to what we see naturally. And that's where we have this Q equals Q naught exponent to the negative KT. And we talked last week that whenever you see this sort of thing, e to the KT or e to the negative KT, that's either a growth function, or in this case, because it's got a negative K, this is a decay function. So it's a mathematical expression that's going to express an exponential decay. In this case, it's an exponential decay in the amount of stream flow that you have in your river at these particular times. So this equation right here, again, is your best fit to the natural data. And a couple of in this case, for your equation, T equals the amount of time since the start of the recession. And K is a constant, a decay constant, and it's going to be unique to each drainage basin. Okay. So really we just have an equation that describes the tail off in discharge in a stream that's due to groundwater. Okay, and that's kind of where we ended last week. Actually, we had one problem where we started and we didn't quite finish. And I asked you this. I asked, what if you don't know the K for the watershed? Because up to that point, we were using K to calculate what the stream flow should be at certain times of the year. And I gave you the K. But if you don't know the K, how do you actually get a K? Well, these are actual variables that are tied to the watershed and calculated from data coming from the watershed. And we can use our Baseflow recession equation to actually figure out what K should be if we have all of the other data. So what you do is you have to figure out K from a previous year's data. And ideally, you'd want to get several years of data and maybe average them out. But one should give you at least something to work with. And then I gave you this example. Q naught, the discharge at the start of the recession. And we'll assume it's on April 1st. And that date can vary according to your watershed from year to year. But for this example, let's assume it's April 1st and that the Q naught is 500 cubic feet per second. And from a previous year's data, you know that the discharge 240 days into the recession is 30 cubic feet per second. So this is about 8 months later. So in the spring, stream's really roaring, 500 cubic feet per second. If you put 500 cubic feet per second in the Poudre River, that would be some pretty decent stream flow. Probably not flooding in most cases, but not something you'd want to wade across. If you go out there, I think today it's probably about 30 or 40. So really the data that I'm giving you right here is probably something similar to what you'd get for the Poudre or a similarly sized mountain stream. Okay, so it's 500 cubic feet per second on April 1st. 8 months later, so much groundwater has been transferred from these alluvial aquifers into the stream. Now we're down to 30 cubic feet per second. What we can do is take our Baseflow recession equation, Q equals Q naught, e to the negative kt. We actually have everything now but k, and we can now solve for k. We did this last week, but I think it's worth going through again. So if we just put down what we know so far, we know that 240 days in, we have a discharge of 30 cubic feet per second. We started out with an initial discharge of 500 cubic feet per second. E to the negative k, which we don't know, but we know t is 240 days. So what we can do is we can rearrange the equation. We start with Q equals Q naught e to the negative kt. We're going to try to isolate down to k. So we can get Q over Q naught equals e to the negative kt. Last week we talked about the way you get rid of the e, the exponent in this, is to multiply both sides by your natural log. And when you do that, ln times e is 1, and you're left with your exponents. So we can just put this in, ln 30 cubic feet per second over 500 cubic feet per second times 1 over 240 days. The units cancel out. That's going to equal your k. And if you multiply this out, you end up with a k that equals 0.0115, and the units are 1 over day. We went through it a little more detailed last week, so you can look back at your notes to see some of these additional steps. Okay, so that's your k. That's how you take this equation, work it sort of backwards with the previous year's data, and get the k for the watershed. And again, all these different watersheds are going to have different k values, depending on what the land cover is like, how big the watershed is, how big the alluvial aquifers are, how porous and permeable the alluvial aquifers are. So it's all this physical stuff that's going on in the basin that's going to determine this K. Okay, so now let's use this equation. I'm going to put it back up. And that's where we ended last week. Q equals Q naught e to the negative kt. So we're going to keep using this. So your next example is Now that you've determined your K, for that particular watershed, what would you expect the discharge to be? Remember, discharge is Q. "40 days into a similar recession, on the same stream." Since it's similar, you can assume that your initial discharge at the start of the recession is again going to equal 500 cubic feet per second. And then you can use the K that you just calculated. So go ahead and see what you can calculate for that. Okay, it's a decay function. So if you got a number greater than 500, you did it wrong. Okay? It's only a month into the recession. So if you think about the curves, you can kind of think about what your ballpark might be. It's going to be less than 500. Obviously more than 0. This isn't very far along, so it's probably closer to 500 than it is to 0. But that depends on your K value. Now, one thing that didn't come up with this example that really pay attention to in future examples, this term right here, negative KT, make sure the K and T cancel out in terms of units. So in other words, they have to be days, 1 over days, hours, 1 over hours. They just need to be units that cancel out. So make sure those two cancel out in terms of units. In this case, our K is in 1 over days. Our time is in days. So they're going to cancel out. That's great. So when you take your K, negative 0.0115, and multiply it by 40 days, e to that quantity should give you 0.631. A little more than a half times 500 should give you a little more than half of 500, a little more than 250, and in this case you get 315. All right, any questions on that? Any problems doing the exponents?
I'm not getting the same answer that you are.
Okay, what are you getting for an answer?
274.4.
274. Anybody else get that? Just want to make sure I didn't do the math. You got 315? All right, you got 0.0115
No.
times 40. You got 0.115?
I got 0.015.
Okay, it'll make a little difference, yeah. Okay, so just the typing in error. That's good. Okay, so another question just to give you a chance to play around with this a little bit. What if next year's recession lasts 9 months? So the snow melt takes a month longer to get going next year for whatever reason. Different weather, whatever. So you have a slightly longer recession. What I want to know is what would the discharge be at the end of that 9 months? And you can just assume 30 days per month to make the math a little easier. Okay, if you run the math through, you're doing 9 months where this is gradually tailing off, and you end up with a pretty low discharge, 22.4 cubic feet per second. I bet if you went down to the Poudre River today, it's actually pretty similar to that. It's probably 20, 30 cubic feet per second. That's a trickle in a stream that size. Now, remember, when you see equations like this designed to mimic nature, these are just best fit. They're best approximations, okay? They have some assumptions built in. You see the shape of this red line? The red line sort of represents what would happen if you ran the times from the beginning to the very end. Is it ever going to hit zero, do you think? You guys have seen mathematical expressions that have that sort of exponential tail off, right? Asymptotic expressions, what don't they ever hit? They never hit zero, do they? So mathematically, you're never going to get zero or below zero with this. Doesn't matter. You could put in 10 billion years, okay? You're not going to get zero. But think about out in nature. Do you think your alluvial aquifers, if they're never replenished with any water, are they eventually going to run out? Yeah. So these equations have limits, okay? So that's just one thing you should always know, is that these are approximations. They have limits. I mean, clearly this mathematical expression is never going to hit zero. That's what this decay function does. It approaches zero but never quite touches. But in real life, yeah, it could certainly be a case where your aquifer could just run completely dry. Okay, so just sort of keep that in mind as you work with these mathematical expressions. Okay, any questions? Okay, that's, I think, about all we're going to do with Baseflow recession for now. I have another concept for you that you may have seen in other classes. We're going to use it here for groundwater. And if you've had hydrology, you probably saw this. It's called the hydrologic equation. And it's simple. And this works for any hydrologic system. And when I'm talking about a system, I could be talking about something like an aquifer, a lake, a stream, a glacier, some sort of physical body that holds water. Okay? That's what we mean by a hydrologic system. Let me give you an example. Let's say we have a reservoir fed by a river, and then the dam can be released into a downstream portion of the same river. So you have a river, you stick a dam on it, and the dam holds back water as a reservoir. Okay, so the reservoir is going to be the system. Okay, so imagine Estes Lake, imagine any impoundment that's held back by a dam. What could be some inputs to that reservoir? Where could the reservoir get some water? Runoff, okay? Runoff. Okay, let's think about that. We could have runoff directly into the reservoir, right? Just off, think about sort of the edges of the reservoir, right? If it rains, water can just run right in there, right? Okay, so you could have direct runoff into the reservoir. But you could also have runoff going into a stream that then feeds into the reservoir, right? So we'll list that as something a little different. We'll do stream flow into the reservoir. How else might the reservoir get some water?
Precipitation.
Raining right on the reservoir, right? So precip onto the reservoir. Okay, so we got stream flow, we got a little bit of runoff, we got rainfall landing on it. Think of anything else?
Groundwater moving in.
There might be some groundwater moving in. Okay, those are all the ones that I thought of. What about outputs? How might the reservoir lose water?
Downstream.
Okay, outflow, stream out, what they let loose and downstream. We'll just call that outflow. Stream flow. You said evaporation. Can I give anything else? Groundwater might be moving out. You don't really know. I haven't given you enough information, but we could have groundwater out. What if your inputs are greater than your outputs? How's the reservoir going to respond? It's going to have more water, right? So in this case, if your input is greater than your output, you're going to have, let me do this, input greater than your output, your storage is going to increase, right? If it's the opposite, if your output is greater than your input, you might have a negative change in storage, and your level will go down. So what we do in hydrology is we try to quantify all of these things as best we can. And that will tell us how our systems are going to respond in the future. And what I want to do is see if I can get this to work. I'm not sure I can get this to work. All right, so I'm just going to write this out. Okay, so I'm going to give you a problem here. So on June 1st, the water in a 140-acre reservoir is 6 feet below the dam spillway. Or in simple terms, that's the top of the dam. The maximum level that your water can reach in your dam, okay? All right, so it's 6 feet below the top on June 1st. All right, let me give you some information about the area. The watershed that feeds this reservoir is 9,000 acres. And that does not include the water, not include the reservoir. So you've got, I'll try to draw a picture out here in a minute. All right, so 18 inches of rainfall on the watershed and reservoir. Over the next 180 days. So over the next 6 months, 1.5 feet of rain falls on the watershed and on the reservoir as well. The area is also subject to 0.5 centimeter of evaporation off the reservoir every day, which is a lot. Okay, a couple more things about this problem. The watershed is in the mountains. And is largely unvegetated. With lots of exposed, unfractured granite. And because of this geology, would you expect much infiltration into the ground? Why or why not? Why not?
The rock is sound.
The rock is, if you've seen granite, there's not much for pores, right? And this is unfractured. There's no plants on it. It's just pretty much bare rock in the mountain. So rain's going to run and land on it, and it's going to run off, right? That's what's going to happen to most of it. Some will evaporate, some will run off. So let me leave you with this. It is, because of the geology, expected that only 10% of the rainfall on the watershed will evaporate or infiltrate. And that leaves 90% to run off. And finally, the amount of groundwater entering or leaving the reservoir because it's solid granite water's not going to move in or move out very easy. We're going to expect it to be negligible. In other words, you can ignore it. Okay, so you have a dam. Behind the dam is a lake. It's 6 feet below the top. Over the next 180 days, 18 inches of rain is going to land. 90% of that is going to run off into the reservoir from a 9,000 acre watershed. If that was the only thing going on, what would happen to the level of the water? It would rise, right? And as a dam manager, you'd want to know how high is it going to rise, right? Because you don't want it to rise and overtop your dam, so you need to release some water. But what else is happening? That's not the only thing going on here, right? You have water leaving the dam, right? Through primarily what? Evaporation, okay? So the question I have for you is, change the color here. As the dam manager, how much water must be released from the dam so that it doesn't overfill? Actually, let me change that part. As a dam manager, you never want it to get so close, okay? So let's say your goal is to keep it at that 6 foot below the top level. So let's go back to that. So let me just get rid of that question. I'm going to change that. Dam so that it stays 6 feet below the top or below the spillway.
So that it stays there, or so that it just doesn't go over?
So by the end of the 180 days, okay, so let me just go on to the next page here. So let's look at this from above. So we've got a, let's see.
It would be okay if it was below 6 feet, it just can't go over.
Yeah, so let's say this is our reservoir. Here's our dam. It's a map view. There's our outflow. This is not obviously going to be the scale, so this is our... Okay, so this is the outline of the watershed. And remember, it's 9,000 acres. Okay. Stream going in, stream going out. Here's your reservoir, which is 140 acres. No groundwater coming in or out. So after 180 days, 18 inches of rain are going to fall in the watershed. 90% is going to end up in the lake. You're going to get some evaporation.
Did you say the watershed was 900 or
1,000.
9,000?
Thank you. Yeah, those decimal points kind of matter. Okay, so the first thing that you do with these sorts of problems is identify all the inputs and outputs. Okay. Now, one final bit here to sort of help you with this is I want you to figure out, okay, as a dam manager, it takes time to let water go, right? You can't just let half the lake go in a second, okay? So you've got 180 days to let go of enough water to keep it at that level. So I want you to do this. I want to know how much you want to let go per second into the outflow. So assume you will release water over 180 days. So that your reservoir is 6 feet below the spillway. At the end of those 180 days. So the real question is, what discharge in cubic feet per second do you have to release during those 6 months? Okay? So what I want to do is give you sort of the rest of the class to work this out, okay? So I'll give you a little while, give you the next half hour or so to work on it, and then I'll go through it with you. So this will be sort of this is a pretty long problem. You know, there's a lot of steps in this, lots of chances for you to play with your conversions and acre feet. Obviously, we're going to have some acre feet going on in here. So it's kind of a way for me to bring together a lot of the stuff that we've done mathematically this semester. If you get hung up along the way, don't fret. It's an